Welcome, everyone. This episode is going to be a summary and review of the first chapter from a book called Coming of Age in the Milky Way by Timothy Ferris. About a year ago, I was having a conversation with my grandmother about how much I was reading recently about space. She pulled this book off the shelf at my grandparents' house, and I dove into it immediately. I was probably about 100 pages in before I found some really outdated pop culture references. I checked the publication date and found it was published in 1988, which was when I quickly realized I rarely read books from before the last 5 or 10 years. Now, nonfiction books being published decades prior only matters if the information within them has been updated or expanded upon, which does happen sometimes in science. There were definitely a few points in the later chapters of the book where I noticed things that could use an update, such as slight differences in estimates for the age of the Earth or the age of the universe. However, I maintain that the first chapter is really well written, where it clearly and in a very engaging way lays out the history of early astronomy, which is no longer changing. This is, of course, a chapter to be taken within the larger context of a full book, but I find the work of early astronomers and scientists fascinating. I think this chapter hits the most important parts, so even if you never pick up the book, I think we can all learn something fun from this episode. This chapter introduces us to the early world of astronomers and their conceptions of how our galaxy and universe work. The basic movements of some objects in our galaxy were straightforward enough for low technology researchers of the time to understand. We did not even need telescopes to measure locations and track paths of the sun, moon, and brightest stars in our night sky. For some examples, ancient astronomers knew the moon took 28 days to revolve around the Earth. They knew that the warmest part of the day took place when the sun was high in the sky, and astronomers across the world during that time had similar observations for some of the other brightest stars in our night sky. However, there were also some things that they were clearly pretty confused about. Ancient astronomers saw objects moving side to side at night, then disappearing during the day. Some of them thought that the stars traveled underneath the Earth by a river during the day and then crossed the sky again the following night. Many academics, including Plato and his student Aristotle, pictured objects moving around using a set of celestial spheres, which caused the sun, moon, and stars to revolve around the Earth. Specifically, they thought this because they thought the Earth naturally stayed in one place while everything else moved around it. As a result, most of those academics spent their time trying to get objects to fit within this celestial sphere theory. The first really famous of these theories came from Eudoxus, whose theory had 27 spheres surrounding the Earth. The next famous celestial sphere model was made by Aristotle for a total of 56 spheres. And another academic of that time, Claudius Ptolemy, was more committed to achieving precise values of where objects would be located in our night sky, rather than coming up with a simple set of spheres. Ptolemy, by the way, is spelled with a P at the beginning. Ptolemy. This guy was more committed to achieving precise values of where objects would be located in our night sky, leading him to utilize these things called eccentrics and epicycles. So those are going to be geometric objects. We can think of them. We can think of one of them as circles within circles, and the other one is going to be rotations within rotations. By having everything move on a series of circles and rotations, he could get them to fit really precise values, even if he did not know why they were going to end up in those exact locations. Ptolemy's expectations of where things ended up oftentimes worked out really well, even if he did not know exactly why they were ending up there. But Ptolemy also fabricated data to better fit his models. And back in that age, checking historical data of where planets and stars were was much more challenging than it is today. So Ptolemy mostly got away with this at the time and became famous, even if he was later on made fun of in other centuries. Part of the reason celestial sphere theory became so popular was because the moon and the sun clearly move across our sky in predictable and repeatable. Is because the moon and the sun clearly move across our sky in predictable and repeatable patterns. And also because the ancient Greeks loved their spheres. As the centuries went on, a few issues popped up, causing some problems in this theory. First of all, most stars and planets would not only move side to side, but also up and down, seemingly at random. Something was happening called a retrograde, which is when a planet seemingly moves backwards and up and down in comparison with its normal route. For example, a planet that's slightly further out than the Earth, Mars, usually looks like it's moving west across our sky from an observer's point of view on Earth. However, when the planets get really close to each other in their orbits, Mars appears to move east for a little bit, and then it goes back to continuing to look like it's moving west across our sky as usual. If you have access to the internet right now, I would encourage you all to Google an image of this briefly, because I could spend a long time trying to explain retrograde, but it's using a picture, it makes a lot more sense. As we know now, Ptolemy's theory was not the correct model of how the universe worked because, of course, the Earth does not stand exactly still with a bunch of spheres moving around it. Occasionally, things fell out of line with Ptolemy's predictions, and that is when he started fabricating data. Near the end of this chapter, the author explains Ptolemy's view that the models had so many exceptions that they probably do not represent the, quote, actual machinery of the universe, end quote, but he thought they rather represented a series of observations. Specifically, Ptolemy said that the, quote, complexities of the model simply reflected those found in the sky, end quote. While I commend him for recognizing and announcing that the universe does not work this way, he had to have realized at some point that better models could have been formed. And he may have better contributed to some of those models if he had not been fabricating data as much. In other words, Ptolemy kept hyping up his sphere theory to explain directly where the stars and planets ended up, even if he was perfectly aware that the stars did not actually revolve around the Earth. While, of course, I'm not the biggest fan of people making up data and pushing theories that they know are false, this is a little similar to the way some modern physicists describe really complex natural phenomena. So a lot of naturally occurring crazy things in physics, we don't necessarily have perfect explanations for. So we tell stories for them. For example, we can talk about 10 or 12 dimensions or string theory at the beginning of our universe to try to explain what was going on. Those stories may not be exactly how the physics shake out, but they are oftentimes useful tools for understanding and explaining what's going on to a wider audience. The utility of those tools sometimes does hold up over time. Even if in the future we get some contradictory evidence saying that string theory is nonsense, that doesn't necessarily take away from the utility of using string theory to explain what's going on at the very, very small scale in our current universe. So rather than considering something really complex like string theory as the truth, we can consider models like this as changeable and continue exploring all possibilities and checking the data whenever possible to provide evidence for or against those theories. With that said, all of this makes me think about the idea that there are definitely going to be discoveries which we can't even conceive of yet. Discoveries that will later on change the course of human history. I have no idea what those discoveries will be, but I'm excited to see what they are and where we end up. Thank you all for listening. I hope you enjoyed this and learned something new, learned something fun today.